So let's say something. Hola. Hola. Oops. Can you say something, please?
Okay. I think now it's
Hola. No, it's not reading this. Okay, let's do something different. Hola. Let's use this. Okay. Sí, dale.
Okay. Well, this is a line of my image. Okay, we'll start with a very, very brief introduction of intermolecular forces, intermolecular interactions, and the role that they play in many chemical and physical processes. And then I will give you an introduction also, because in 2 hours it's impossible to cover all the methods, the quantum mechanical methods to investigate, to study intermolecular interactions, because this is a very wide topic. Okay, we will need maybe the whole school to explain everything. Okay, so I will give you some insight of the most important schemes to investigate intermolecular interactions. Is the variational scheme, and the perturbation theory. Okay, I will focus in perturbation theory. We'll focus on the symmetry-active perturbation theory, which is probably the most standard method to study intermolecular interactions, and the method that gives you more insight. Okay, but it's computationally very expensive. That's the problem. Okay, and then I will introduce you in this perturbational scheme, which is based on electron deformation density, which is a scheme we have developed in Vigo. Okay, it's a perturbational scheme because we split the interaction energy in different components using second order perturbation theory. Okay, but it's also we can see that it's a hybrid method because we use also variational scheme to obtain the electrostatic and Pauli attachment. Okay, and finally, probably this in the afternoon, okay, in the practical lesson, I will introduce you to the program EDA NCI, which was developed also in Vigo, where this perturbational scheme is implemented. Okay. Well, you know that, starting with the introduction, you know that, okay, the molecular charge distributions, the electrons and nuclei, okay, but this interaction goes, you know, perfectly that goes beyond the molecules. As a result, interactions between different molecules that alter the properties. Okay, this is the interaction between electrons and nuclei from different molecules. So this is much more complicated to deal with than the interaction in molecules, intramolecular interactions. Why? Because the distance between electrons, okay, is larger if we study an intermolecular complex, okay, than the distances between electrons in a molecule, okay. So we need to describe very well the long-range electron coronation, okay, and this is a very difficult task. We can do it with wave function methods, okay, very well, but with a very high computational cost, and we do it approximately using BFT methods. Okay, we will talk about this in detail. So intermolecular interactions we are going to talk about are interactions between closed cell systems. They are called non-covalent interactions. Okay, the difference with the covalent interactions is that the covalent interactions are, of course, in open shell systems. Okay, so covalent bond, normally you have 2 radical pieces, okay, and you have paired electrons, and then you pair the electrons, and you have a very energetic interaction. okay, the covalent bond, mainly because of exchange, electron exchange, okay. And in this case, in the closed cell system, the electron exchange is repulsive, as we will see. Okay, so they are very different interactions. Okay, interactions between electrons and nuclei, but the nature is completely different. Okay, so are these intermolecular interactions important? Crucial, but not important. Very, very important. Okay, why are they very, very important? Because they play a crucial role in many chemical and physical processes. For example, they govern the phase transitions. You know, from a condensed phase to a gas phase, for example. Okay, they play a key role in molecular aggregation. Okay, for example, in the formation of micelles and colloids. Okay, this is because they form because of intermolecular interactions. They play a very important role in subphase and interphase processes. For example, a simple absorption process in physics absorption is due to intermolecular interactions between the subphase, the atoms of the subphase, and the molecules. Okay, that are absorbed on. And you know that moving to a more biological questions, they play they govern the protein folding and DNA arrangement, and also they are very important in membrane permeation. For example, in biological membranes, cell membranes. Okay, when a drug is crossing the cell membrane, the crossing depends on the interactions between the. For example, suppose that we are a bilayer lipid membrane between the lipid and the drug, but also in synthetic membranes. Okay, for example, for water cleaning membranes that take the molecules, the toxic, the contaminants, or something like that. This is because of intermolecular interactions. Okay, and of course, probably the most important processes are the solvation processes. This process depends strongly on the intermolecular interactions. Okay. So, how to deal with intermolecular interactions? How we can study intermolecular interactions? We can study intermolecular interactions classically. Well, we can do it if we have intermolecular interactions that are mainly electrostatic, because with multiple expansions we can investigate. With multiple expansions, we can investigate the intermolecular interactions between multiples and between multiples of different fragments of molecules. Okay, so electrostatic interactions between multiples can be represented classically, but we know that other interactions have a clear quantum origin. For example, which intermolecular interactions depends on has a quantum origin, so cannot be represented classically. For example, dispersion can be represented classically. No. Dispersion depends on what? On electron correlation. Not any electron correlation. The long-range electron correlation. The electron correlation between electrons from one molecule and the other molecule. Okay. Pauli repulsion. The Pauli repulsion. The repulsion depends on the exchange, but the exchange is quantum origin. Okay. So how we can do with classical methods to deal with this dispersion and Pauli interactions, with parameterization, with potentials? Okay, we can do it, but how we optimize these potentials and how we obtain these parameters? From quantum mechanical methods. Okay, so use of quantum theory to evaluate intermolecular interactions and analyze their nature is necessary. Okay, so another question is, okay, I can obtain the value of interaction, the energy of intermolecular interaction. But this gives me insight, or give me just a number. It gives me just a number, the strength of the interaction. Okay, but the intermolecular interactions may be very different in origin. The nature can be very different. Okay, some of them are mainly electrostatic, and others are dispersive, inductive, etc. So, if we want to extrapolate to large systems, for example, using molecular mechanics, so the constructive potential to describe this dispersion and Pauli repulsion, etc. It's very important to decompose the interaction energy into different different terms with different physical origin. I'm talking about electrostatic, inductive, dispersive, and repulsive interactions. Okay, so in this way, then we can obtain, we can derive potentials to describe any of these contributions. Okay, so let's talk about this decomposition of the interaction energy, which is called energy decomposition analysis (EDA). Okay, but energy decomposition analysis can be also applied on in covalent bonds, intramolecular, the problem in bonds in molecules. Okay. So I prefer to talk about interaction energy decomposition analysis. This is what we are going to talk about. I'm not going to talk about the energy decomposition analysis of covalent bonds or intermolecular bonds. Okay. Well, we have a classification here of this kind of interactions. First, we have the electrostatic interactions. You know, these are my molecules or my fragments. I also prefer to talk about fragments than molecules. Why? Because maybe I'm interested in studying the interaction between a solid, an ion or a cation, with all the water molecules. So in this case, my fragments are, in one case, it's a molecule, the cation or an ion, but in the other case, is all the water molecules, the solvent. So electrostatic interactions between fragments. Okay, a solvation process of an ion is mainly electrostatic. Okay, also interaction between dipoles, charged dipole interactions. Well, inductive interactions. So you know that the systems fragments polarize each other. There is a polarization, a formation of dipoles or quadrupoles, multipoles. Okay, induced by the potential created by the other fragment. Okay, then we have interaction between these induced multipoles. We have induction interactions. And dispersion interactions. Well, dispersion interactions is an interaction that only has a quantum origin. Okay, so there is not a classical equivalent to dispersion. And you know that or maybe you don't know, but tell you that dispersion interaction are only originated in electron correlation between electrons of different fragments. Okay, so these two interactions, induction and dispersion, are normally included in just one, which is called polarization. Why? Because the inductive interaction and dispersion interactions both polarize the system. Okay, so these electrostatic interactions are interactions between the frozen electron densities of the fragments. Okay, so when we study, we talk about electrostatic energy. Electrostatic energy is between the frozen. Where we take two fragments, put it in the complex. Okay, in the geometry of the complex, and then we don't leave the system to relax the electrons. So, and we analyze the electrostatic interactions. That's why in non-polar molecules, non-polar systems, we don't have electrostatic interaction. Okay. Well, electrostatic polarization, these are long range. Okay. But then we have other kind of interactions, like short range interactions, okay, which the most important one is the Pauli repulsion, the repulsion interaction. And this has also a quantum origin. And it's originated in the electron exchange between electrons from one fragment and the other fragment. If they are closed cell, okay, we have in quantum mechanics, we have the Pauli exclusion principle, and you know that the same spin electrons experience a repulsion, but the repulsion only originated in the spin. It's not a Coulomb repulsion. Okay, so perfectly know that two electrons in the spin cannot occupy the same point in space. So there is a repulsion where we have an electron with alpha spin. We cannot have another electron with alpha spin. Okay, and due to this Pauli exclusion principle, we have this repulsion. Okay, the density change the energy of the system change. And also we have additionally to this repulsion due to the change in the electron density of the fragments, we have the exchange energy between electrons of different fragments. Okay? So in the Pauli repulsion, we have two components: the repulsive one and the exchange. Repulsive is positive energy, and exchange is always negative energy. What happens in an open shell system? The exchange energy is much larger than the repulsive energy, so I have an stabilization due to Pauli effects. What happens in a closed cell? The other way around. What I have is the repulsive term is much larger than the exchange, so I have a repulsive interaction, a positive energy. Okay, and now then we have also other kind of interactions, which are sometimes you define it, I think, like hydrogen bonds and charge transfer. Because what is a hydrogen bond? A hydrogen bond is a combination of many things. The electrostatic part, also partially covalent. So, okay, and what is charge transfer? To define the charge transfer is always arbitrary. So I will not talk about hydrogen bonds and charge transfer. Only these physical terms that are clear origin. Okay. Well. Some illustrative example of long range. Why I talk about long range and short range? Okay, this system is polychlorinated dioxin, tetrachloro-dibenzodioxin, TCDD. One is the most toxic dioxin in nature. Okay, maybe you know the was the president of Ukraine, I think he was poisoned with this TCDD. I don't know if you know, I don't remember the name. Yeah, okay, thank you. So he was poisoned with this TCDD. So this is taken from a study where we investigated with Juanjo, collaboration with Juanjo, we investigated the permeation of TCDD in a lipid layer. Okay, so simulating a cell membrane. And well, this is in this permeation process. What you have is a minimum of free energy minimum in the middle of the membrane. Okay, we investigated the intermolecular interactions in this free energy medium. Okay, with QM hybrid methods. This is just the representation of the QM region. In the middle, you cannot see it well, okay, because there are many atoms here, but in the middle, there is the TCD molecule, and these are DOPC molecules, lipids, okay. I think in this system, there are 9 DOPC molecules, okay. Well, this is a representation, ACE, sorry, represent the Pauli repulsion density. So I said that when you have Pauli repulsion, there is a change in the electron density, mainly where the change in the electron density happens in the overlap between the electron densities of one fragment and the other. In this, when we have an overlap of same spin electrons from one fragment and the other, I have a reflection of the charge because I have in this region because I have a repulsion, Pauli repulsion. Okay, and here we are representing this deformation of the density due to the Pauli repulsion. You will do some kind of plots with, of course, a very smaller system in the practical exercise in the afternoon. Okay, so in ACE, I have changing the cutoff for the representation of the density. So I change it from 10 power -4, 10 to -5, and then 10 to -6 here. Of course, here the density, as I can see, it's larger and larger if I reduce the cutoff. Okay, and this is the same for the polarization. This is the change in the electron density of the fragments due to polarization, dispersion plus induction. And It's exactly the same representation that you can see. The difference in this case is the most interesting one with the lowest cutoff. You can see that the interaction involves here the whole system, the whole coherent region. And in this case, only a small part. So where the overlap between the fragments is important. Okay, this is source range. Okay, range of interaction is smaller here than here. Okay, it's just an illustrative example of this classification. Well, so it's clear that intermolecular interactions are normally weak. They are weak, of course, compared with a covalent bond. We are talking about, in this previous example, of around 14 kilocals per mole. Okay, the interaction between the TCDD and these lipid molecules. And you know that covalent bond is much more. Okay, it's 100 kilocals. It depends on the covalent bond, of course, but around that. So are weak, but are very important. How we investigate or calculate the interaction energy? But normally, the simplest method is the supermolecule method. Okay, in the supermolecule method, I calculate the interaction energy as the difference between the energy of the complex, energy of two fragments, relaxed, etc., optimized, okay, minus the energies of the fragments isolated. Okay. This is the definition of the interaction energy. In the definition of the interaction energy, these isolated fragments, the geometry of these fragments is not relaxed. It's the same geometry as they have in the complex. Okay, this is not all the energy involved in an interaction. We have something more, that is the energy associated to the relaxation of the geometries of the fragments to the most stable, okay, conform disposition geometry. If I include this energy, which also tends to stabilize the isolated fragments with respect to the complex, I talk about the binding energy. So binding energy includes this relaxation of the geometries. Interaction energy does not include it. Sometimes this energy, relaxation energy, is called the preparation energy in some methods. Okay, if you listen on preparation energy is the relaxation, the energy associated to relaxation of the isolated fragments. Well, with the supermolecule methods, I get a number, okay, for the whole interaction energy. It's very simple, it's straightforward because I can do it at any computational level, okay? But it has two important problems. The first one is the physical understanding. Understanding is almost nothing because I don't get any information, any insight about the nature of the interaction. Okay, I don't know, it's mainly electrostatic, if this person plays an important role, etc., etc. Okay, so only gives me a number. This is not interesting. It's not useful if, for example, I want to use my results to parameterize force fields, for example, in molecular mechanics, parameterize Pauli or the dispersion in molecular mechanics. And another problem is associated to the basis set size, the dependence of the energy in a quantum mechanical calculation with the basis set size used. No, this is in the case of intermolecular interactions is dramatic sometimes, and it's called the basis set superposition error. Right. I would like to stop a little bit here on this basis set superposition error and comment something about it. Well, what is the origin of basis set superposition error? If my energy of the complex and the isolated fragments depends on the basis set size, when I calculate the energy of the complex, okay, the basis set I'm using for the fragment A, or for the fragment B, both we have the fragments A and B, okay, is the full basis set of the complex. So to calculate the energy of one of the fragments, I use the basis of the other fragment, okay, because I'm calculating the complex with full basis set, okay, the basis of located in all the atoms. And when I calculate the isolated fragments, I am just using, of course, the basis of this fragment. So the energies of the fragments in the complex are improved because of the use of the basis set of the other fragment. This is the basis set superposition error. The origin is exactly the same as the problem of the basis set size, okay, dependence of the energy. When this basis set superposition error is negligible, when I have a very large basis set. When I have a very large basis set, the basis set problem, size problem, disappear, okay? And of course, the same for the basis set superposition error. So in an infinite basis set, I will not have basis set superposition error, okay? How can I, for example, solve the problem of the basis set superposition error? Extrapolate to a complete basis set limit. If you know what is the extrapolation complete basis set, CBS limit. Okay, but this is many times very costly, so computationally not feasible. Okay, so another solution, not so good, but not so good as the other one, as the extrapolation to infinite basis set, is the counterpoint. Okay. In the counterpoint method, what we do in the counterpoint method? So what we do is to calculate the energies of the fragments A and B using, in parentheses, is represented the basis set, using the basis set of the complex. Okay. So I include the basis set of the other fragment in the calculation of fragment B, in the calculation of A, and vice versa. How to proceed in Gaussian, for example, we will do it in the afternoon in the computational exercise. We introduce in Gaussian and in other softwares too, but we are going to use Gaussian. Okay, for example, this is the Cartesian coordinates for the water dimer. Okay, we introduce ghost atoms. The ghost atoms are atoms that doesn't have electrons, don't have nuclei, charges, okay, but only bases. Is this a good solution? Is an exact solution? No, it's not an exact solution, because it's true, many authors suspect that it overcorrects, and I can tell you that it overcorrects the basis set superposition error. So the counterpoint method overestimates the effect of the basis set superposition error. The basis set superposition error always gives us an interaction energy lower than the real interaction energy, a more stable complex than the complex without a basis set superposition error. And in this case, we obtain with the counterpoint method an interaction energy slightly larger, so slightly less stable complex than the real. Okay, but we have to use it because we avoid the large computational cost of this extrapolation to CBS limit, and the basis set superposition error in large systems can be even larger than the interaction energy itself. So we have to use it. Well, let's talk about now of the EDA schemes, of the energy decomposition analysis scheme. It's variational, perturbation theory, and the perturbational scheme I'm going to talk about at the end. Okay, so we have first the variational approaches. These were the first ones from the 17th. The most famous one is the Morokumas energy decomposition analysis, but Morokumas was initially developed for Hartree-Fock. Then it was It was applied on DFT many years later, okay, because you know that in Hartree-Fock we don't have electron correlation. So, for example, we neglect completely the dispersion energy. So, well, variational approaches where the formation of the complex is divided into several steps, each one associated to a given effect, exchange or without relaxation. We are obtaining variationally the wave function in each step, okay? And we calculate the energy of obtaining one step with one wave function in one step, previous step. So we are cutting the interaction energy pieces, okay? Obtaining from these intermediate wave functions, variationally obtained. Then, the best method to investigate intermolecular interactions is perturbation theory, because if an interaction energy is small, normally it's a small effect. Perturbation theory here is perfect, because we can treat the perturbation, okay? We can treat the interaction, the intermolecular interaction as a perturbation to the energy of our reference system, where our reference system are non-interacting molecules, okay? So this is the best method to study non-covalent interactions, and we get a lot of insight from it. Okay. And finally, this scheme, which is, in my view, is good because computationally is very cheap and gives you also a lot of insight, and can be applied also to post-SCF methods, because it's based on the deformation of 1 and 2 electron densities. And as far as I can calculate these densities, I can use any computational level to apply it. Okay. Well, let's start with the variational approach. Just some fundamental ideas to use the fundamental of the method. Variational schemes are many, okay, different, with small differences. In one, calculates the charge transfer interaction, energy due to charge transfer in the different ways. So, okay, there are many. I'm going to give you some insight on the most extended one. Probably is the one developed by parents and people from Netherlands, and it's implemented in the ADF software. Okay, if someone works with intermolecular interactions, probably knows this EDA scheme implemented in the Amsterdam Decomposition code. Well, what we do here? We consider two fragments, A and B, which form a complex, okay, and then we have first the electrostatic energy. The electrostatic energy is this way to understand the electrostatic energy is, I would say, universal, because the electrostatic energy is the only term that, if you apply the same electronic structure method to obtain your wave functions, densities, whatever, okay, you will obtain exactly the same electrostatic energy if you use variational, perturbational, or other schemes. Okay. So in the electrostatic energy, A and B, we consider A and B with four frozen charge distributions, though they are brought together from the infinite to the position they occupy in the complex. And the wave function in this step is just the product, the Hartree product of the wave functions. So we don't leave the electrons from the beginning, from one fragment and from the other fragment, also the nuclei interact. So there is no electron relaxation. Okay. So with this frozen electron distribution, I calculate all the electrostatic terms. This one, for example, the first one, is the core attraction between the nuclei from fragment A and the electrons, represented by the electron density, of the fragment B. This is the same from core attraction of nuclei from B to electrons of A. This is the Coulomb repulsion, okay, between electrons from A and B. And finally, we have the interaction between the nuclei from A and B. Okay, this is the electrostatic interaction. Very simple idea, very simple to take. Of course, if we have a very, very, very weak intermolecular interaction, okay, the electrostatic, the relaxation orbital, the electron relaxation will be very small, and the electrostatic energy, okay, is even a good approximation to also induction and all other electrostatic energy, also the induction of the charge induced dipole is also an electrostatic interaction. But we take it out from this electrostatic energy because we have a polarization. Okay, but if the polarization is very small, we include all electrostatic interactions within the electrostatic. Well, the Pauli repulsion. How we calculate the Pauli repulsion variational in the variational approach. So if we have an overlap between the electron densities of fragment A and fragment B, molecule A and molecule B, you know that the Hartree product is not violates the antisymmetry principle. Okay, if we don't have overlap, we don't have exchange between electrons A and B, and the Hartree product is exact. Okay, the function can be represented exactly in this way. But if we have an overlap, even if we don't leave the electrons to relax because of the interactions between electrons and nuclei from A and B, we need that our wave function, reference wave function, do not violate does not violate the antisymmetry principle. So to calculate the Pauli repulsion, what we do is to antisymmetrize the Hartree product. But we antisymmetrize the Hartree product without leaving the electrons to relax. Okay, in the frozen electron densities of A and B. As I told you before, if we have a closed cell interaction between closed cell systems, A and B are closed cells, this is a repulsion step because we have the repulsion energy plus the exchange between electrons of fragment A and B. And the repulsion energy governs the Pauli interaction. And finally, we have the last step in the variational scheme, which is relaxation of the electrons. Okay, now we leave the electrons and nuclei from fragment A and B to interact. Okay, and now we have, of course, a polarization of the electron density of A and B and orbital relaxation. This is normally in these schemes called orbital relaxation because they associate in this scheme this interaction to the orbitals. And it's possible to decompose this part of the interaction energy in orbital contributions. Okay, how the unperturbed orbitals before the interaction change when I have the complex in the complex. Okay. This interaction, this orbital relaxation, which is called also this is a polarization energy. In this variational scheme can be also divided in polarization and charge transfer. So the orbital relax, but there can be also an electron transfer from orbitals, occupied orbitals of fragment A or molecule A to unoccupied orbitals of B and vice versa. Okay, so this charge transfer can be also obtained in an arbitrary. Well, this is a summary of the steps in a variational scheme. First, we have the relaxed wave functions of A and B. In the initial, this is the initial state. And now what we have is to calculate the electrostatic. We put the two molecules, two fragments in the geometry of the complex. Okay, no relaxation. The difference, the energy difference between this wave function, the Hartree product, and this wave function, which is the energy of the isolated systems calculated separately. Okay, this is the electrostatic energy. Then we antisymmetrize the Hartree product, this Hartree product. Okay, you can see that the deformation is okay, but the same spin electrons tends to migrate from the overlap region to avoid the overlapping. Okay, the difference, the energy difference between the Hamiltonian applied on this wave function and this wave function is the Pauli energy. And finally, we have the real wave function, the complex wave function. After orbital relaxation, it's this one, and we calculate the energy of the complex, and the difference with respect to this step is the polarization of the orbital relaxation. How we can decompose further this in charge transfer and induction, and charge transfer and polarization, because since this scheme was originally developed for Hartree-Fock, we didn't have dispersion, so we have only induction and polarization. We can do is first from this step to this one is to leave the relaxation, orbital relaxation, but without transfer of electrons from the occupied orbitals of A to the virtual orbitals and occupied orbitals of B, and from occupied orbitals of B to unoccupied orbitals of A. So we avoid the charge transfer. If we avoid the charge transfer, what we are obtaining is polarization energy free of charge transfer. This is a hypothetical state, because this is some arbitrary, okay? Because this situation here is of course impossible. If the polarization takes place in one step, so it's orbital relaxation and charge transfer. But we can split this polarization in these two terms. And how is this would be the polarization without charge transfer? And finally, if I leave the relaxation, orbital relaxation with charge transfer, the difference is the polarization energy. Oh, sorry, the charge transfer energy. Well, what happened with the dispersion energy in a variational scheme? Because variational schemes always rely on single determinant wave functions. Okay, we can do it at Hartree-Fock level, Hartree-Fock wave function, or we can do it with DFT. So we have the Coin-Shan DFT, we have Coin-Shan wave function. Okay. So first, in Hartree-Fock, well, in Hartree-Fock, we have electrostatic Paulian polarization, which is only induction. Okay, let's forget about this charge transfer, because there are other schemes. There's different schemes to represent this charge transfer. Sometimes some arbitrary, and it's my opinion. I don't like to match the to calculate the charge transfer, because it depends of arbitrary constraints. Well, electrostatic Paulian polarization. This is what you have, orbital polarization. What you have, for example, in this EDA scheme, the ADF program. Okay, so we don't have dispersion, because no correlation in Hartree-Fock. We don't have long-range electron correlation, no dispersion. Well, what we can do is to calculate also the interaction energy with the supermolecular approach at correlated level. For example, molar pressed or couple clustered. MB2, for example, or MB4 or CCSD, CCSDT. Okay, interaction energy. So the difference, you can say that the difference between the interaction energy at correlated level and the interaction energy for Hartree-Fock, we can say that this is the missing term in Hartree-Fock, which is dispersion. Is this correct? No. Why is not correct? Because, okay, dispersion energy is there, because we know that dispersion energy, long-range electron correlation, is well represented in for example, in MP2 or MP4 or CC methods. But we also, when we calculate interaction energy at correlated level, we are including also here short range and medium range electron correlation. Okay, and this short range and medium range electron correlation changes also the electrostatic energy, so we'll see later, changes also the Pauli repulsion, changes also the induction energy, changes everything. So here in this difference, okay, we have all the correlation, all the effects of electron correlation. So it's not only dispersion. And sometimes the other effects I'm talking about is short range electron correlation, medium range are even more important than dispersion. Okay, this is not dispersion. It's a way to correct our Hartree-Fock EDA scheme with electron correlation. We cannot assign this energy difference to dispersion. What happened with DFT? Well, with DFT, we know that with DFT we don't have only electrostatic polymerization of the previous step, because with DFT we are including short range and long range. Short range and medium range electron correlation in some cases. In some functionals, DFT functionals, only short range electron correlation. In other functionals, we also correlate, for example, these Minnesota functionals and O, etc. These functionals, some of them, include pretty well the medium range electron correlation, and you will see it in the exercise, in the computation exercise, because we are going to compare the performance of this unique functional with M06 to X. Okay. But what happened? The difference between the DFT energy and the Hartree-Fock energy, internationally, is not dispersion, because most of DFT functional fails to describe long-range electron correlation and fails to describe the dispersion energy. What we do in DFT to correct dispersion energy? Include what? What we include in DFT? Sorry? Thank you.
You add the exchange correlation.
You can improve your potential, okay, but it's not only it improves the result, but normally it's not a good result. We include this empirical correction. Empirical correction, for example, and it's necessary to include it in all DFT functions, because some authors, some developers of DFT functions say, no, my functional includes the dispersion is parameterized with dispersion-free error, etc. It's not true, and you will see it in the afternoon. Okay, there are much better functionals, good functionals, others that are poorer for the dispersion, but there is no one functional free of dispersion error. Maybe for your set of complexes very small, but if you move to for example, to study an absorption process with many atoms there, you will see that you have a dispersion error. Okay. Well, this is the aspect what we can do with DFT to include these empirical corrections. But these empirical corrections, be careful with these empirical corrections, because you include the correction in the energy, but you don't include the correction in the density. Yeah, talking about DFT. Why? Because this is a post-SCF correction. So this correction is included in the calculation of the gradients, okay, but not in the SCF procedure. So if you calculate the polarization density of, for example, benzene dimer with B3 lip, okay, and B3 lip D with dispersion, with empirical dispersion correction, you will see that your densities are exactly the same. Okay, the energy is not the same because you introduce this term in Hamiltonian. Okay, but this term, okay, don't operate on your wave function, constant wave function. So the wave function doesn't change. Okay. Well, this is the shape of dispersion correction. For example, Riemann. You have damping functions. These are damping functions. These are functions, and then you have coefficients. Okay, I'm going to get into detail here because I think I have other questions to explain. Okay, I don't know what time is it.
12:30. So you talk for 15 minutes.
Okay, 10 minutes, and we can do a break.
One question. So when you add the correction, the 3, the 2, Then you do the difference between the Hartree-Fock energy, and so this is still not the dispersion term. It's because I saw like, okay, we do the difference, and it arises this term that is the dispersion.
You know,
and keep going.
It's a very nice question because you know that for Hartree-Fock you have this correction too for Hartree-Fock and for DFT functionals, and this is parameterized to get a very good interaction energy. Okay, but you correct, okay, mainly dispersion, but you correct everything. Okay, you correct everything. So it's true that you are correct. You cannot say this is only dispersion. No, it's dispersion, and the failing includes also the failing of Hartree-Fock in, for example, other electrocorrelation effects.
So long range and short range correlation effects, it should be better to see like that than dispersion.
Yeah.
More careful.
Yeah.
Okay. Thank you.
But probably many people don't like what I have said.
Yeah,
but
because I never
listened
about it. Yeah.
The important thing is it's clear. I have with Hartree-Fock, I have not only the problem of long range electrocorrelation, I have also the problem of short range electrocorrelation. And for example, in electrostatic energy, I start with a reference wave function, this Hartree-Fock, which is wrong because it's a correlated wave function. So I have an error there. With this correction, I am also including this effect here because my parameters are optimized to get the very good interaction energy. Okay. Well, what's the solution? CCSET or high-level methods, but these are computationally feasible. Well, let's talk about perturbation theory. This is the most beautiful theory, okay, but it has also the problem that the computational cost is large. Okay. So let's start with the simplest one, which is the Riemann Schrödinger perturbation theory. This is also called the perturbation theory without overlapping. Okay. Let's start with a problem where I have an interaction, molecular interaction, where I don't have short-range energy. So I don't have Pauli. Okay. So there's no overlapping. I don't have to antisymmetrize my reference wave function. Okay. And then we will introduce the problem of the antisymmetrization. So what we have here in perturbation theory, that of course in the zero order Hamiltonian I have here is the summation of the Hamiltonians of A and B.
Marcos, you said you want to do the break or not? I didn't understand.
I want a break, but in
after the
5 minutes or something like that.
Okay, sure. Sorry, I understood.
When I have to talk for 1 hour. Okay.
Yeah, sure.
Well, this is a summation of the A and B Hamiltonians plus V. This V is the intermolecular interaction. It's all the terms in the Hamiltonian that involves electrons and nuclei from different fragments. Okay, very simple. Can I apply here the perturbation theory? Yes, because V is much smaller than the reference Hamiltonian. So the interaction is small. Okay. Perturbation theory is very nice up to second order. For higher orders, it becomes a mess sometimes. So it's much more complicated, and the application is much more expensive. Okay. So I will focus on second order perturbation. Well, the reference system considers very selective molecule. The perturbation corresponds to the interaction. Okay, so I can obtain the reference energy from the Hamiltonian of the fragment, isolated fragments, and then I have my reference wave function, which is exactly the same wave function, variational. The starting wave function is variational. Okay, so there are many common things in between the two methods, two schemes. Well, if I apply perturbation theory up to second order, okay, I think you really know the perturbation theory. So at least the students that come from the Master of Theoretical Chemistry, for sure. So avoiding this overlap, okay, this RSPT without overlapping between the molecules. Where I have the first order term is electrostatic energy. You know that the first order term in perturbation theory involves the unperturbed wave function, okay, the zero order wave function, okay, and the perturbation. And this is exactly the definition of electrostatic energy. It's the same definition as in the variational scheme, exactly the same. Okay. Now, in second order, I'm going to move to second order. I have this expression here. What I use here is the first order correction, first order corrected wave function, okay, and also perturbation. And I have this expression here that can be split in different terms. I have a summation here of all the possible excitations from the ground state configuration, for example, in fragment A, from 0, ground state, to different state configuration A. Okay, and also for the and also for the fragment B or molecule B, all the possible stations, okay, from the ground state to the excited state configuration. Okay. And this summation involves all, but any of them can be at the same time can be 0. Okay. Well, if I split this summation, I can split the summation in 3 different terms. The first one suppose only the excitations, only excitations in the fragment A, and the fragment B stays in the ground state. Okay. So all excitations in the fragment A. This is the induction energy because it's the polarization of fragment A due to the electron distribution, unperturbed electron distribution of fragment B. Okay, I polarize only this one. So this is induction. It's like in classical theory is the permanent dipole, induced dipole. Okay. Now I have also the induction in B, the same. Okay, but changing the fragments. And now I have other terms which involves excitations in A and B at the same time. This is induced dipole. Induced dipole, okay, is what we call, well, with the analogy in classical theory of the dispersion interaction. Okay, normally in classical theory we say fluctuating dipole with induced dipole. So interactions between excitation, sorry, in both fragments. This is the dispersion energy, and you can understand now that dispersion energy can only be defined in perturbation theory, because in variational scheme we don't have now. Okay, we need perturbation theory to define dispersion. Okay, exactly. I mean, well, what are the problems here? Okay, all the problems here are those associated to the fact that there is an overlapping between normally the interaction overlapping between electrons of A and B, and this simplified perturbation theory without overlapping doesn't work. Okay. Maybe we can stop now, 5 minutes. I'm very slow.
One question, is the air conditioning okay or is that inside?
Si cojo algo de la tarde, castigáis si cojo algo de la tarde.
Ah, no, eso, las 2 horas como tú quieras.
No voy a acelerar. No voy a acelerar.
El tiempo no tenemos pasado porque tenemos una plancha baja.
Sí.
Vamos a las 8.
Sí, matamos, ¿no? Sí, pues siempre que sí, ¿no? Siempre que sí. Sí. Yo le pregunto hola. quería preguntar por lo de la dispersión, y como te comentaba la chica, yo no lo había escuchado nunca, ni había visto, y no sé si hay alguna bibliografía, algo que
Sobre la dispersión, ¿a qué te refieres?
sobre las correcciones empíricas.
empíricas.
Sí.
Que si quieres me...
Te puedo escribir por
Sí,
correo.
es que por correo yo te mando.
Vale.
Vale, pero bueno, mi idea es principalmente que eso que ves, porque muchas veces en muchos trabajos computacionales ves que hablan de la energía de dispersión como esa parte siempre de la forma empírica. Está claro que la mayor parte está ahí concentrada, pero después
Claro. Yo tenía entendido que ya estaba, se creó una corrección, como que ya estaba eso incluida dentro del estadístico, pero por lo que veo, no del todo.
yo te mando, me escribes y te mando, te busco, te selecciono algunos, porque ahí hay,
Sí, claro.
hay mucha cosa.
Claro. Muchas gracias.
Y no, porque yo he visto también muchas veces que funciona que está deslocalization. Es lo mismo, porque como que cada esquema le llaman la inducción y deslocalization.
Ah, porque hay, vale, tú me estás hablando, por ejemplo, de NDO. Esquema. Es que claro, es que hay muchos esquemas en los que lo dividen.
Vale.
Es que tú tienes la polarización. Lo que está clarísimo y que no es nada arbitrario es la polarización. La polarización está bien clara. Luego hay divides y hay esquemas en donde, por ejemplo, lo que vamos a usar, nosotros usamos en Vigo, saca la inducción con la perturbación segundo orden. Entonces sé que tengo la inducción segundo orden. ¿Y luego qué tengo ahí? Pues tengo la dispersión. Si mi interacción estuviera bien descrita, que no es muy fuerte, con segundo orden, lo otro puedo decir, que es dispersión, y si no, tengo dispersión, tengo más cosas. Luego hay gente, o sea, luego es esquemas que sacan la transferencia de carga. Así la sacas en el esquema variacional más típico, pero por ejemplo en el NDO, la teoría de natural con órbita, ahí también lo saca de una forma diferente. Y luego hay gente eso que dice, bueno, la parte de la localización siempre, o sea, no hay ninguna crítica, es todo lo contrario, siempre si te da insight, ¿sabes? Si tú tienes una información en la que puedes, digamos, explicar y encontrar diferencias entre unos complejos y otros, genial. Pero
Empieza de complicado, le llaman distinto.
hay un montón, eso es lo que yo decía. Aquí necesitaríamos una semana, gente que te viniera con su esquema y cada uno te cuenta su esquema. ¿Sabes?
Pero sí que coordinan el lado
No, yo me fui a... Es así.
part because I was in the radio system. So you check the interactions using the radio system. You can do some kind of like interaction analysis. Which kind of intermolecular interaction, like you can study using
So you can study all of them.
so what is that?
Okay, if you are sometimes you are in the middle of
Specifically that ETSC.
So you can say
And kind of specifically to correct the kind of directions so we can do it.
empezamos, ¿eh?
Sí, sí, cuando quieras tú. No, miramos si 6, 7, no, si quieres 5 y luego otros 5, así que es que tenemos la reserva para poder.
Okay. Let's go on. I have to go faster because otherwise I will not be able to cover everything. Well, the problem, anti-symmetrization. We need to anti-symmetrize our wave function. Of course, we need to include the repulsion, the Pauli repulsion. Okay. How we do that? Well, there's different strategies, but the most standard is the symmetry lateral perturbation theory. Okay, this is complicated theory. I'm going to give you some fundamental ideas. I'm not going to get into detail of each of the terms. Okay, if someone is interested, I can give you references, very good bibliographic references of this method. Well, if we now anti-symmetrize the wave function, okay, and we calculate the different energy terms, the electrostatic energy, the first, well, not the electrostatic energy, the first order energy and the second order energies, okay, with an anti-symmetrized wave function, the symmetrization process is more or less complicated, okay? But if I have my anti-symmetrized wave function, then I can obtain all the energy terms with the correct wave function, this anti-symmetrized wave function. And now the energies I have is the electrostatic energy. The difference between the energy with the anti-symmetrized wave function and the Hartree product first order is exchange correction to the electrostatic energy, and this exchange correction to the electrostatic energy is the Pauli energy, the Pauli repulsion. Okay, because it's the same idea in the variational scheme. Now I use the anti-symmetrized wave function as reference. Okay, apply perturbation theory. First order energy includes the exchange correction, okay, the Pauli repulsion, and also the electrostatic energy. I can separate both. So I have two terms, two first order terms. And in second order, it's actually the same. I have induction energy I have dispersion energy, and I have the exchange correction to induction, and the exchange correction to dispersion. This is what I get from symmetry and anti-perturbation order, theory, up to second order. Okay. I have also, I can also apply perturbation theory to third order. It complicates much more the problem. So the solution includes, at third order, for example, includes not only exchange, not only induction and dispersion, but also crossed terms, so coupled terms between induction and dispersion. Induction polarization energy, the splitting of polarization energy, induction, dispersion is only possible at second order. Okay, third order, I have a combination of induction and dispersion. They are not separated. Well, this is for a monodeterminant wave function. So my reference wave function was Hartree-Fock. There's something interesting here that I am using Hartree-Fock as reference in perturbation, in the symmetry of the perturbation theory, and Hartree-Fock, but I have dispersion energy. Why I have dispersion energy? Because in my perturbation theory, okay, they allow me to couple the excitations in the different monomers, in the different molecules. So this is correlation. This is long range correlation. So I am including long range correlation because of my perturbation scheme, but I'm not including intramolecular electron correlation because the reference wave functions are obtained at Hartree-Fock level. So I have to correct the effect of intramolecular correlation, okay, in the method. So how I do that? Well, what we do is a double perturbation scheme. So we have two perturbation operators. V is the intermolecular one, and W here is the intramolecular one. This is, this W operator is the perturbation operator in, for example, Moller-Blessed method. Okay. And in this double perturbation scheme, everything is more complicated, of course. I have many terms because I have terms that depends of the order or perturbation, intermolecular perturbation and intramolecular one. So the intramolecular is the electron correlation. Okay. So we have two superintegers here in this summation. I indicate the order of the intermolecular interaction, and J indicates the order of the intramolecular correlation expansion. So we can also normally in SAP what you use for intramolecular electron correlation is MP2 theory, but you can use also couple cluster. But this is very, very expensive. You can only study complexes with such very small number of electrons. So normally what you do is sub PT doesn't level second order in intramonomer electron correlation. Okay, so we have these terms, all these terms for the interaction energy. Let's start step by step. First, Hartree-Fock. In Hartree-Fock, we have electrostatic, symmetry rapid, I mean. We have exchange, we have induction, we have exchange induction, and this delta Hartree-Fock, it is included in all the programs that it has SAP implemented, includes all the higher order terms. All the order terms higher than 2 are computationally very expensive. Okay, so how we solve that? We calculate the interaction energy using the supermolecule approach, and now we subtract this interaction energy, okay, from the summation of all the terms in the perturbation scheme, okay, except the dispersion energy. Why? Because we don't, in the supermolecule approach using Hartree-Fock, we don't have dispersion. So we remove dispersion, and now we subtract the interaction energy using the supermolecule approach, which includes all the rest of the terms, electrostatic, Pauli, and induction up to infinite order in perturbation. And we subtracted from these terms, and this is called the delta Hartree Fock. This is supposed to include all the higher order terms, the order for order, etc., which are normally very small if interaction is weak. Okay. Now we include also dispersion at Hartree Fock level, and now if we go to a correlated sub, okay, now we include also these other terms that include also the corrections of the intramonomer electron correlation, corrections to the exchange, electrostatic induction, and also dispersion, and so on. Okay. So many terms we have there. So that's why I say that you get a lot of insight, because we decompose your interaction in many small pieces. Okay. Well, the costly of sub wave function, using wave functions, including intra-monomer electron correction, is very large. So it's very expensive method. So can we use DFT instead of wave function methods, instead of MP2, for example? Because we know that DFT includes intramolecular electron correlation, and with some functionals better than others, but include part of the electron correlation. Okay. So what we do in sub-DFT, is computationally much more efficient than the sub-wave function, wave functions. What we do here is for the first order terms, for the electrostatic and Pauli, we replace the Hartree Fock orbitals by coefficient orbitals. These coefficient orbitals are supposed to be correlated orbitals, no? Or are corrected from intramolecular electron correlation. But if we do this also for the second order terms, since Hartree Fock, since in DFT we don't include long range electron correlation, we have parameters. Our dispersion and induction, but especially dispersion, are not very good. I don't obtain good results. Okay. So what can we do? What we do in that sub-DFT is complicate even more the solution by using couple perturbed Conish-Sham and time-dependent couple perturbed Conish-Sham, which is equivalent to time-dependent DFT. Okay, you know these methods. I think most of you know couple perturbed Conish-Sham and time-dependent DFT for the second order terms. With couple perturbed Conish-Sham, what we obtain is the static response function. Okay, and with the static response function, we have an exact expression to calculate induction. Okay, we use in sub-DFT this expression of induction in terms of this static response function obtained with couple perturbed Conish-Sham. Okay, and calculate the induction energy from this expression. And in the here. Okay, and with the time-dependent couple perturbed Conish-Sham, okay, what we obtain is the frequency-dependent response function, and from the frequency-dependent response function, we can obtain an exact expression for dispersion. Okay, so dispersion is obtained from time-dependent couple perturbed Conish-Sham, time-dependent DFT. Okay, and induction is obtained from couple perturbed Conish-Sham. This complicates the computation, so the method is and the implementation is more complicated, but the results are quite good because the computational efficiency of time-dependent DFT and couple perturbed Conish-Sham is very good. Okay. Well, we have another problem here, which is the exchange correlation potential, the decay with the distance of the exchange correlation potential, okay, the asymptotic behavior of the exchange correlation potentials, which is normally in DFT functions very bad. And what we do here is to do an asymptotic correction. So we correct in sub-DFT the decay of the exchange correlation potential with the distance, because normally the exchange correlation potential decay very fast. That's why the long range electron correlation is not well described by them. Okay, and we correct this decay of the exchange correlation potential to improve our results. Okay. Well, what we have here in sub-DFT is exactly the same terms as in Hartree-Fock, okay, but obtained in a different way. First order, summarizing, first order terms from Konisham orbitals replaced in Hartree-Fock or Konisham, induction from couple-perturbed Konisham theory, dispersion from time-dependent couple-perturbed Konisham theory, and also to improve the results, the asymptotic behavior of the decay, of the exchange correlation potential. Avantage is cheaper than many body perturbation theory sub, so the MP2, for example, sub. Asymptotic induction dispersion to second order are potentially sub. Why are they potentially sub? Because they are obtained from exact expressions. But what is the problem? They are exact. If my functional is exact, the functional is not exact, so I have this is the problem. But if I have the exact functional, exact exchange correlation potential, okay, I will obtain the exact induction and dispersion. Well, it's great accuracy. It's the computational. The accuracy is similar to MP2 sub, and it's cheaper computationally. It's faster. But what are the problems? So we have a great dependence with exchange correlation potential between DFT. This is always with DFT. Exchange corrections are not exact. Okay, and it's difficult to extend to system with more than units. Well, this is difficult in all ADA schemes. And well, no, there is no optimizations today, so only single point calculation. These are problems that this class problem is very easily solved because I can calculate the complex first, the geometry of the energy of the complex. First, this calculation take this geometry to the sub-DFT partition. Well, this is a comparison of different functionals. I'm just showing that, this plot because you can see here how the asymptotic corrections, improve the results. Okay, this is the mean and sign interactive errors with respect to a couple cluster sum. Okay. Well, this is an example of an output from the sub program. You have implemented sub at least in MolePro, and then you have the sub program developed by the sub developers. Okay, and this is an output file. And you can see that you have many terms here. Okay, and well, this is a comparison also the results obtained using sub-DFT for the interaction of chlorine and sodium with this is a cookie ball. Okay, notice like a ball. This system. This is not a coronin. The coronin will be with a benzene ring in the middle, and with different substituents here. This Cora is hydrogen, Cora met is methyl, X is methyl, fluorine or cyanide. And well, I'm showing you this plot to see that how the EVA scheme can give you insight, because if you change these substituents, you see that the difference in the total energy is blue light. Okay, the total energy is just a number, and tells you that with cyanide is the most stable complex. But the energy compositionality tells you why. You can see that all the terms are more or less the same except the electrostatic energy. And why is that? Because if we are chemists, we will say, okay, the cyanide is mesomeric, it has a mesomeric effect. No, it takes some electrons from the system, conjugative system, and accumulate it here. So I am including the positive electrostatic potential. I have a positive electrostatic potential here in the middle. So it interacts very well with anions, but it's the other way around in the case of of cations. Okay, so with just a calculation of interaction energy, I can say, okay, I suppose that this is because of mesomeric effects, some qualitative ideas, but with the energy composition analysis, I have a quantitative proof, okay, of that. The static energy increases, and you don't change too much. Okay, now how much I can have?
You have 35.
55 minutes for our scheme. Not fair. Okay, now I'm going to talk about the scheme, the perturbation scheme we have developed in Vigo, and the one you are going to use in this afternoon, the computational exercise. Okay, well, most of the ideas. Okay, this is not completely new, so it's based on variational schemes and on perturbational in perturbational theory. So I think I can go always fast. The idea here is, well, let's try to develop a method which is computational efficient, that I can apply at any computational level, okay, and give me the same insight as the other schemes, no? Particularly the perturbation in the perturbation field. So let's associate the different energy terms: electrostatic, power, induction, and dispersion. In principle, electrostatic power and polarization with the deformation density. It's a scheme based on electron densities and the electron density and its deformation. You know that the Hamiltonian is constructed we have one electron and two electron terms, and okay, the energy is then a functional, okay, of the one electron density and the pair electron density. Here, from the one electron density, we obtain the kinetic energy, one electron terms, kinetic energy and the core attraction, and from the two electron density, we obtain the exchange and the Coulomb repulsion, the exchange and the correlation. Okay, so if the energy is a function of these two densities, okay, the interaction energy, which is the difference between the complex energy and the monomers, isolated monomers energies, is a function of all of these, which are the unperturbed electron density, one electron density of A and B. Okay, the unperturbed two electron density of A and B, and the corresponding changes of these densities when the complex is formed. Okay, so this is the formation density. The question is, can the formation density be employed to fragment interaction into physically meaningful terms? Okay, we are going how this deformation density. Simply, we can also split it in the deformation density due to Pauli and the deformation density due to polarization. And how we do that? Well, this is the expression of the energy as functional. I told you that it's a functional of the density of the one electron density and the two electron density. Okay, this is expression of the energy. Well, this is also this is a functional really. These are called it's a functional. It's implicitly. What means that I don't use here for the kinetic energy. You know that the kinetic energy is functional is unknown. Okay. This is the base of Konigshamn DFT. So this is a functional of the density matrix, one electron density matrix, know the density. Okay, but it doesn't matter because I can work with density. I can work with density matrix. I don't mind. I can talk about deformation of density. I can talk about deformation of density matrix. Okay. Well, I have all these terms. Instead of the two electron density, I have split the two electron density in the unconditional probability and conditional probabilities. You know that the two electron density give us a probability of finding two electrons with an electron point in R1 and the other electron in R2. And these have two components. That is the unconditional probability, so the products of the one electron probabilities and the exchange correlation. Okay. Exchange correlation density. Well, this is the energy, this is the nuclear term, and now what I'm going to do is to partition the operators and the densities, okay, in intramolecular and intermolecular. Okay, first the simplest, the nuclear repulsion. Nuclear repulsion term, I can talk about nuclear repulsion with intramolecular in fragment A, fragment B, and the intermolecular between the nuclei from different fragments. Okay. Now, the nuclear potential operator. This is the potential created by the nucleus. Okay, and I can split it simply in the summation of the nuclear potential operator of A and B. Okay. Now, the density, the one electron density. I can say that the electron density is a summation as a result of the electron densities of my reference, which are the isolated A and B fragments, plus the deformation density due to the Pauli repulsion. This is the one I showed you in this image before when we talked about short and long range Pauli deformation density with polarization deformation density. This is the deformation density, and now that due to the polarization, to the orbital relaxation, okay? The induction, dispersion, and higher order terms in a perturbational scheme. And I can do exactly the same exchange correlation density. We will see later that this exchange correlation density, Hartree-Fock, is easy to obtain, but post-Hartree-Fock, it's a very hard task. We do an approximation in our quite good, I think. Well, I can do the same. Exchange correlation density in a perturbate with A and B, the exchange, intermolecular exchange, but with the unperturbed systems, before the orbital relaxation, and now how the exchange correlation density changes when the electrons relax. Well, if I introduce, of course, I introduce this partitioning in the previous expression. Okay, in this one, I have this gigantic equation, nothing gigantic, but the terms are very clear. I have only to put my partition and see how many terms I get. Where this energy, the complex, of course, is the summation of the energy of the energy of the isolated system plus the interaction energy. This is what I want to obtain, the interaction energy. Since these terms associated to AA and AB, sorry, to EA and EP, are very easily to obtain, to identify here: the kinetic energy, the core attraction, intramolecular core attraction, this one and this one, the intramolecular repulsion, this one and this one. I can remove all these terms from here and obtain an expression for the interaction energy, which is still large. No? But all these terms here have a physical interpretation because I can group these terms in terms associated to electrostatic interaction, because you remember the expression of the electrostatic interaction before, all these terms are here. I can also identify the Pauli repulsion, the repulsion energy due to Pauli. In fact, this is the terms here, for example, all this is this one, and this one, okay, and also this one for the kinetic energy. This is the repulsion. This is the energy, kinetic energy and potential energy associated to the change in the density due to the repulsion. This is the repulsion energy. And then the exchange is here. It's this term here. Okay. So, and the electrostatic terms are the most easy to obtain. You to identify this one, the core attraction, and now the electron repulsion, and now the nuclear. So, if I group all these terms, I will obtain the electrostatic energy, the repulsion energy, the exchange, the summation of repulsion exchange is the Pauli energy, okay? And now I have two terms that, okay, we have grouped this in deformation energy and exchange correlation. Deformation energy is the deformation energy, polarization energy associated to the one electron density, and the part of the polarization energy associated to the to electron pulse, or the exchange correlation, density. Okay, I have this partition. Okay, these two terms is the polarization energy. These two terms here is these two terms here is the power. Well, just some comments about how to obtain the delicate point here is how to obtain the Pauli deformation energy. Sorry, the Pauli deformation density. Deformation density due to Pauli, especially for post-Hartley fog. Because for Hartley fog is simple, but for post-Hartley fog, we have to introduce some approximations. So how to obtain Hartley fog, SCF, okay? Hartley fog that we do the same for DFT using the Conian orbitals instead of the Hartley fog. So this is for monodeterminantal wavefunctions. So we know that the exchange energy, the exchange energy is the difference between the two electron density minus the unconditional probability, which is the product of the one electron densities. Okay, this is the exchange density. So this is a quantum effect. You just change. Well, in Hartley fog, we can exactly represent the exchange density with an orbital basis. Okay, these are the Hartley fog orbitals. So I'm going to go fast with this because okay, this maybe I should explain in more detail. I don't know how much slide you have in density matrices and these kind of things. Well, if I transform this basis into the atomic orbital basis of basis set, you can express the exchange density using the density, the one electron density matrices, okay, and the atomic orbital basis. This is an exact expression. Okay, how we do to obtain the part corresponding to the intermolecular exchange? Okay, we have here a problem because okay for the exchange density at Hartley fog level, we can express this as the summation of the exchange density. We say that before. The exchange density of the isolated molecule A, the exchange density for the isolated molecule fragment B, and now the part we want to obtain is this one, the intermolecular part. This is obtained with the unperturbed orbitals of A and B, and the question is how can I obtain this one? Because we could say, well, we can use this basis, with this orbital basis, the same unperturbed orbitals, no? And now exchange electrons between the orbitals of A and B. But what is the problem? These orbitals are not orthogonal, so this basis is not orthogonal. If the basis is not orthogonal, I have a very important problem here. So what we do is to orthogonalize first these orbitals of A and B, the occupied orbitals, are orthogonalized, and now with this orthogonalized basis, we can represent the exchange energy, the total exchange energy of the complex using this basis. Okay, this orthogonal basis. Well, this process of organization solves two problems. First, how to obtain the exchange density, intermolecular exchange density, and also how to obtain the one electron deformation density. Okay, because these orthogonalized orbitals already account for the repulsion, the Pauli repulsion effect. And now from this, now I can obtain easily the intermolecular exchange, Hartley fog exchange, okay, with these density matrices, and the orbital basis is of course the same, and also the one electron Pauli repulsion density, okay, from this density matrix. So the plot I showed you before for this TVDD with the OPC molecules was a representation of this function, this density. Okay. So the problem is in post-Hartley, post-SCF. Time?
20 minutes.
I have 20 minutes.
Yes.
That's a lot. Okay. How to obtain the Pauli deformation density? Okay, this is we have a problem here. The problem. What is the problem? So in principle, now I have exchange and correlation. So this is exchange correlation density instead of exchange density only. Okay, but the problem here is that I don't have a simple way to represent this matrix. Okay, so the two electron, this depends on the two electron density matrix, and the two electron density matrix for a multi-determinant wave function, it's huge because it's a matrix of 4 indices. Okay, and I include there all the possible cyclic configurations instead of only the occupy the Hartree-Fock ground state. So there is no programs that gives you this the 2 electron density matrix for systems with many electrons, and I have to work with systems with many electrons. So what we do is to extrapolate an expression for the exchange correlation density at post-SCF level, which is exact for 2 electron systems. You can say, okay, 2 electron systems, 2 electron systems to a multi-electron system. Okay, the results are quite good in my opinion. Okay, we would like to try. There are many things to do in research, and we don't have many time, but we would like to try other functionals of this type to the other approximation to this exchange correlation density. The idea is to work with natural orbitals. You know what the natural orbitals are. Those that diagonalize the density, possessive density matrix. Okay, but we use a similar expression to a Hartree-Fock, to SCF, but using natural orbitals, which include electron correlation. These are correlated orbitals. The expression is very similar, but now you know that in natural orbitals we have occupation numbers. In Hartree-Fock we have, because it's said, we have to see 2, always occupation number is 2. Okay, but here we have occupation numbers, no integral occupation numbers, and we have this is a weight. The occupation number is the weight of the orbital in the wave function expansion. Okay, we have to include these weights in the expression of the exchange correlation density, and we need to include it in a way that this density is n-representable. So integration of the density can give me the number of electrons, and the simplest way to do it is with these occupation numbers, the square of the occupation numbers. Okay, this is, I repeat, it's exact for 2 electron systems. Of course, an approximation for multi-electron systems. So with this idea, we do exactly the same that in Hartree-Fock SCF, with a difference. In the orthogonalization process, because I have natural orbitals of fragment A and natural orbitals of fragment B, they are non-orthogonal. I have to orthogonalize them. In the orthogonalization process, it's more complicated. Because now I have to do a weight orthogonalization because the natural orbitals, all the natural orbitals don't have the same weight. In Hartree-Fock, they have exactly the same weight. Patient number is the same. So the weight orthogonalization is similar to that done in the NBO method. Those that work with NBO or have some analysis with NBO would do maybe that. Well, this is how we solve the problem of post SCF methods. The question is, if I want to go to if I want to study large systems with many electrons, couple cluster, I cannot use couple clusters. So all of this I have said is not relevant because normally for large systems we have to use DFT. Okay, but for small complexes, small molecules, we can apply this methodology for post-SCF methods. This is a comparison between hydrogen dimer, water dimer, hydrogen fluoride dimer, and the methane dimer. Okay, these are hydrogen bonded systems, large electrostatic energy, contribution of dispersion is small, and this is completely the opposite. No? We have a highly dispersive complex here. The methane complex is stable because of dispersion energy. It's a low-polar system. And this is a comparison between the most delicate terms are, of course, the most delicate term is the Pauli portion energy. Okay, we compare the electrostatic and the exchange repulsions of the Pauli energy between our scheme, this scheme, proportional scheme, and the SAP. Using exactly the same levels, I mean, Hartree-Fock, SAP Hartree-Fock, SCF, MP2, and couple cluster, and we do the same, okay, the same geometries. We don't change the geometry also here, because, for example, in methane dimer, there is no Hartree-Fock geometry because it's not stable Hartree-Fock, because no dispersion, the complex is not stable, the methane dimer, using Hartree-Fock, and we use it of the CCSD geometry. So you can see the electrostatic energy between SAP and our scheme is practically the same. It has to be the same because definition is the same. Okay. So difference is because numerical questions. Implementation. Okay, so this is the percentage of deviation, and now we have the most delicate point is here. So the exchange repulsion between SAP and our scheme at SCF level, it's very good, pretty good. Why? Because our exchange density is exact using Hartree-Fock. Okay. So there are differences because in SAP you use you apply an antisymmetrizer and you antisymmetrize the wave function in different ways. So small difference. But now the problem is what happens with post-SCF methods where we are using approximation. Well, the differences I think are not so relevant. Especially in the most delicate system, which is a methane dimer, the results are very, very, very close. So we don't have a large deviation. So, well, and computationally speaking, computational time difference is gigantic, it's enormous because SAP couple cluster takes, I don't know, I don't have data of time there, but it's much more expensive than our scheme. Our scheme is quite fast. The calculations maybe takes 5 seconds for the energy decomposition analysis, 5 seconds for these systems, no more. The limiting step is the calculation of the reference, because we use couple classes as CCSD with a large basis set, it will take time. But the energy composition analysis, the partition of the interaction energy, takes 5 seconds. Well, okay, the comparison is good. Okay, perfect. What happens with the second order terms? Okay, with second order terms, with the polarization energy. No? Well, the polarization energy, the most interesting system is methane dimer, and we focus on this dimer. You can see, well, first, comparison between our method only, no comparison with SAP, STF, CCSD. Now, we know with STF, the methane dimer is not stable, the interaction energy is positive. Okay, and we can see that the electrostatic energy doesn't change much when going from STF to CCSD. It's very small, the electrostatic energy, because classically it should be zero. In quantum mechanics, it's not zero because the overlapping between the molecules has associated an electrostatic energy. We can talk about this if you want. But, okay, it's almost zero, but it's not zero. The difference is small. Now, the Pauli repulsion energy. This is a spectral result. CCSD is larger than SCF in all cases. Why? They have the same geometry. This means that the overlap between the electron densities of the two molecules, two monomers, is larger than CCSD in correlated method than in an uncorrelated one. Does it make sense? What happens with the electron correlation? What happens with the mean distance between electrons when I compare a correlated wave function with an uncorrelated one? Why the couple CCSD energy is lower than the Hartree-Fock energy? Many. Why? Because of repulsion. The repulsion energy is overestimated in Hartree-Fock. And this is the main problem of Hartree-Fock. It's overestimated because the electrons they're not correlated, and we use this mean potential. The electrons are closer they predict that the electrons may be closer than the reality when you include the correlation, electron correlation. So in this case, the intramolecular density, spread of intermolecular density takes more space in the case of correlated methods than in the uncorrelated ones. So the overlapping is larger. So the polar repulsion is larger. And it happens always in these complexes and any other complex. And finally, polarization energy. We don't have induction here because the non-polar system, the induction energy is, the polarization energy is practically zero in STF and minus 0.81 in CCSD. This is dispersion energy. Okay. So it seems that it works. Well, this is more the same. I'm going to explain very fast, okay, how we can split our polarization energy into induction and dispersion. And it's a very simple idea. Induction and dispersion, the splitting of the polarization into induction and dispersion, the exact splitting is second order perturbation theory. Okay. This is the polarization energy we have. These two terms, this one and this one. Induction energy is not. It has a classical analogy. It's not related to correlation. So I forget about this exchange, correlation, deformation, and I focus on this deformation energy in the polarization energy. And I will going to focus on these two terms, which is the charge induction energy. I call this charge induction energy. This is the interaction of the A potential and B potential. These potentials are the nuclear potential plus the electrons, potential created by the electrons. I include this potential here. So here in this term, I will show very fast, but I will show you that it's included induction energy. And how we do this, how we extract induction energy for this term? First, this is the expression of induction energy in perturbation theory. It's the same expression I showed you before, but now it's the expression in terms of transition densities. These densities, rho B and rho A, L, O, and O are transition densities. Transition density from the ground state to an excited state M in B and also in A. This is the expression of induction energy. First, we calculate the deformation of polarization energy using its second order using the perturbation theory. Okay, and now we introduce this deformation density up to second order into our charge induction energy here. Okay, then after some algebra, okay, we extract the expression of the induction energy that we have here. Okay, so this induction energy has the expected shape because you can see that this the potential created by the perturbed monomer A interacting with the polarization density of B, and the other one, the term B interacting with the electron, the change in the electron density of A. But the interesting point here is that this is multiplied by 1/2. Okay, and this is this has a corresponding with induction energy defined classically, because if you have studied intermolecular interaction and you have introduced in the classical expression of, for example, dipole induced dipole interaction, the classical result is that the induction and a dipole induction dipole interaction, half of the energy is lost in induction process. So if these are not these are interaction not between induced polarization density induced. This is an interaction of, for example, dipole, permanent dipole. This 1/2 doesn't appear in the expression. Okay, this should be electrostatic interaction between dipoles. But when we talk about induced dipoles, induced multipoles, okay, we have also this 1/2 multiplied here because half of the induction is lost in the Transfer of the energy, sorry, it was an induction process. So it's nice that we recover the classical result, because induction energy has classical origin. Okay. So, and the rest of polarization, if I get the induction energy, the rest of polarization is the dispersion plus the higher order terms. If my interaction is weak, and second order perturbation theory describes well the interaction, I can say safely that this is dispersion. Okay, because polarization is induction plus dispersion. Okay, but if I have a stronger interaction, I can say that this is rest pole includes higher order terms. Okay. Well, this is the partition we have finally here with this exchange and rep is a power. Is a power exchange. Well, time.
2 minutes.
2 minutes. I only need one. Okay, the hybrid method. This is the school, not schools about multi-layer. Well, the hybrid QMMM EDA. I have 2 minutes for that.
Yeah.
Okay, what we do in the good point of this method is easily to implement, to extend to QMMM calculations. Okay, you know that there are other EDA's EDA schemes that can be applied to QMMM hybrid methods, but the recipe of these methods is different than ours, and I will show you that they don't give you the correct terms. Normally, well, as far as I know, no scheme partition the interaction for QMM calculations in the same way as we do. Well, the recipe followed in these schemes, in most of the schemes, is, well, we locate interaction center within the QM region. Okay. We let the MM atoms to polarize the QM region, so we calculate the complex. For example, in our scheme, we calculate the complex, the density of the complex using a QM methods. Okay, so I'm including the polarization of the QM region by the MM potential. Okay, and then what most of the schemes do, I think all of the schemes except ours, define fragments within the QM region and perform the QM EDA. So they don't include the potential, this potential, which is included in the Hamiltonian when performing the calculations, the QM calculations in the EDA's partition. Okay, the QM region is polarized, so it's not the same as doing a QM EDA without the MM potential, because our densities are different. Okay, but they don't include the potential within the expression of the electrostatic energy, induction energy, etc., etc. Should we include the potential in the EDA to obtain good results, or it's not necessary? Because if my QM region is large, is very large, maybe it's not necessary. But for the small QM regions, you can find difference. So this is an example of, this is the ammonium. These calculations were done by Alvaro, who is here. This is the ammonium surrounded by 100 water molecules, okay? And this is a comparison of a QM EDA. The calculations of the complex and isolated fragments densities were done both with QM. So they are exactly the same densities. But in one case, in the first case, we do a QM EDA, and then in the second case, we do a QM EDA, so including them and potential in all the terms. And you can see the differences. Well, the total interaction energy is the same. Of course, it's the same. Because in the supermolecular approach, what I do for the interaction energies, energy of the complex minus energy of the isolated fragments. And the calculations, the previous calculations performed to obtain these results are exactly the same. Okay, so the total is the same, but the partition is wrong in the first case. You can see the electrostatic energy is minus 140.6, okay? And doing it the correct way, okay, including the potential in the EDA scheme. Also, the electrostatic energy changes 40 kilocalories per mole. It's a lot. And you see the power is the same. Why power is the same? Because so range, so power and potential doesn't matter. Okay. The polarization, the induction changes, but the induction is very small here. Okay. And dispersion, the dispersion and the higher order terms are those that are most affected by change. So doing it this way, I am transferring electrostatic energy to the dispersion term. Okay, doing the correct way, this doesn't happen. So it is underestimating the electrostatic energy. Of course, it's underestimating the electrostatic energy because I'm not including in my EDA partition the charges and dipoles of the MM atoms. Okay. Well, I'm finished now. So only how we do in our scheme how to include this potential is the potential of the atoms of the MM region. Okay, we do it in a simple way. We include it in the nuclear potential operator. Remember the nuclear potential operator? Well, the fragment that has the MM region, because in the previous example I have one fragment is the ammonium cation, and the other fragment is called the water molecules in the QM region and the water molecules in the MM region, which are, I don't remember how many molecules, 1,000, more than 1,000 in the MM region. Okay, many. Well, we included in the nuclear potential, and now all the terms. This nuclear potential is included in the electrostatic energy, in the induction energy, in dispersion, all the terms. Okay, so it's quite simple to do it. Well, this is an example finished now that how important is to use hybrid methods in the energy decomposition analysis. This is a comparison of the electrostatic energy and the dispersion energy for adenine solvated by N water molecules. We are going in the QM region. We are going from 0 to 250 water molecules in the QM region. The red line it's a QM, pure QM EDA, pure QM. So no as the previous slide. So I don't do a QMMM calculation previously to obtain the electron density. So QM, only quantum mechanics. And this is the result, the blue line using QMMM. You can see that the convergence is much faster. So that means that I need to obtain a good result with QM, pure QM. I need maybe 100 or more molecules to obtain a good electrostatic energy, but only with 50, including the M region, the electrostatic energy conversion. Okay. Well, of course, in dispersion not so long range. As the electrostatic energy, the convergence is okay in both cases. Well, everybody is starving, so I think I can stop here.
It was more than 2 minutes.
What?
It was more than 2 minutes.
Yeah. Well, okay, we can stop here. Maybe in the afternoon I can, because here also I have the last part is only 2 slides. Because this is the explanation of the program, the calculations we are going to do with this program in the exercise of the afternoon. Okay. Well.
So we have questions. Yeah, some minutes for questions if you want.
You have some minutes for questions.
No. We don't have, but I have to say.
Okay.
Okay, so anyway, in the afternoon.
We can talk in the afternoon. I think the afternoon will be more relaxed.
Okay. So we go back to the PC room at 20 to 4. As usual, as it in the series.
De ahí también saca aquellos los MCI plots y todo eso, ¿o no? Es
Yo
diferente.
creo que es un análisis de Julio.
Sí, sí.
Es diferente. El ejemplo es muy interesante porque te distingue de una tableta de interacciones, pero es más cualitativo.
Sí, pero no es porque yo enseñé ahí.
No, porque porque hablo de no probar eso es lo que yo decía al principio, que una decomposición análisis, hay una decomposición análisis pero esto es para no cover interaction. No es porque son cover interaction.
Sí, gracias.
Podemos dejar aquí las cosas de seguridad para la presida, que es la web. Bueno, ¿cómo está bien el aeropuerto? Esto es mejor llevarlo porque luego ya vamos para el otro aula. Bueno, van a volver a ir, ¿sabes? Pero podemos dejarlo si no es lo que decir con la mochila para el restaurante y luego volvemos.
También lo hago yo.
Como tú me digas, si la dejamos.
Sí, lo dejamos.
Cierras aquí, ¿no?
Sí, aquí queda cerrado.
Salimos fuera, ¿no? A la calle.
Sí, vamos a ir a la calle, dice abrigados. Lo que sí, vamos a dejar desconectado esto ya. Muy bien. ¿Tienes alguna predilección?
Sí, dale. Porque lo que hemos encontrado es que, sobre todo, lo que hemos mucho también es fijarnos luego las densidades.